Hi, in this video, I am going to explain MMC based AC/DC converter using half bridge submodule topology. Now, in this system, I am using 8 submodule in upper arm and 8 submodule in lower arm, and I'm using a 3-phase rectifier. So, in this setup, currently the output voltage is set to 3.6 kV. We can change the reference of this as per our need. The control structure that I have used in is DQ vector based control, which is PI plus decoupling. So this is the MMC model overview, that we have a 3-phase grid, and each phase is having upper arm and lower arm, and each arm contains 8 half bridge submodules, and those are connected with an limit circulating current within using an inductor. So in total there are 48 half bridge submodules across 3 phases, and this is the overall model, and we are using the half bridge. So with the half bridge topology, we have two switches, S1 and S2, and anti-parallel collecting diodes, and there's a output capacitor that is connected across the this half bridge topology. Let me show you. So this is my model, and in this model, the load is connected at the output side, which is the RL load. This is the output current, and this is the output voltage. This is our rectifier, uh, or the converter circuit diagram. Here you can see that we are using the 8 uh, signals, the capacitor voltage signals that are going into this VCAU. Let me show you from the inside. So from the inside, you can see that we have around 8 submodules. So if I can zoom in to show you, so we zoom out to show you. So there are 8 submodules connected in series, and we are measuring the arm currents. So the arm current is IAU for the A phase upper arm, and for the A phase lower arm it is IAL. Similarly for the B phase it is IBU and IBL and ICU and ICL. So we are measuring these currents, the arm current, and these are the submodule voltages. So each arm contains 8 submodules. So you can see there are 8 signals going in, and in total there are 48 number of submodules. So this is a detailed model of the uh, MMC based AC/DC rectifier. Here you can see that there are total 48 signals that are coming. Why 48? Because inside each we are using a NOT gate. So if you don't want to use this here, we can directly, you know, connect a NOT gate outside this, and we can just send the signal. This will make the system complex. So to avoid that, we are using the NOT gates inside this each arm, and just to make the circuit simpler. All right, so this is our circuit. Yeah, the transformer is connected, which is a step down transformer. So this is our 3-phase grid, which is a 50 hertz, and the voltage of this grid is about 23 kV. So this is step downs. This is a step down transformer, two winding step down transformer. So it is step down the voltage around 10 kV, from 23 kV to 10 kV, and 500 MVA transformer is there. So this is our overall circuit diagram. Now let me explain the control structure. So we are taking the grid voltages and the currents as an input, transforming them from using the ABC to the DC transformation. And then we have a DC voltage outer loop where we provide the VDC reference. So here you can see that in the control part, here you can see that we have a grid voltage, grid current, and the reference, voltage. This is the reference voltage, and this is the mired voltage. So their difference is taken and given to the PI controller for the control purpose. Then we have a decoupling plus feed forward using the omega L cross coupling, and that is the output of this is transferred to the DQ to ABC for the normalized and the substitution purpose, right? For the VDC bus, we used PLL obviously, and DQ current inner loop. We have a voltage limiter block is there, which limits the voltage to the VDC by 2, and then those reference signals are generated. So the each block is separately discussed here. That we use the Park transformation and the clock transformation, right? For the control purpose, because the both gives us VD, VQ, and ID, IQ, and these are the DC components. So it is very, you know, it becomes very easy to control those parameters. In the next step, we have a DC voltage auto loop. It generates the ID ref. So basically, the VDC ref, which is the 3.6 kV, and we have a VDC mired. So the error is given to the PI controller, right? And yeah, this is one of the thing that the scholars do while they are preparing for the you know MMC based rectifier, that they need to provide this minus sign. Otherwise, if this minus sign is not given, then you will be getting wrong output voltage, or you'll see oscillations. Nothing will work fine in that case, right? So in the step 3, we have a DQ current inner loop, right? In the fourth state, we have a decoupling plus the grid feed forward, right? And in the fifth stage, we have a voltage magnitude limiter. We limit the voltage to the half of the DC bus, right? Where we find the magnitude using the VD square and the VQ square, and the limit is set if the V magnitude is greater than the Vmax. Scale both, right, to prevent the overmodulation. Next, we use the DQ to ABC inverse transformation, so to generate the reference signals so that they can be used in the you know PWM state, right? Then we have a voltage balancing algorithm, which is the conventional voltage balancing algorithm. Uh, so it can be seen here. So this block generates basically the modulating signals or the switching signals. So we have the 8 submodules, and each submodule, sorry, we have 6 basically arms, the upper arm and the lower arm. So this will generate a reference signal which will start from the 0 and it will reach up to 8 because we have 8 submodules. So those signals will go inside this voltage balancing and gate pulsing algorithm. So here you can see we have each separate control for the arm. So the V capacitor, which is the capacitor voltages of the upper arm phase A, the arm current, and the reference signal, and this enabling signal is there. And inside this, we have a sorting and state generating algorithm for each phase. So this is how the this basically converter works. This is our output voltage. Currently it is set 3.6 kV. Let's say we are interested in 3 kV. So we can change the reference and we can run the simulation, and we can see that our converter will generate now the voltage which is around 3 kV, and the capacitor voltages will be according to that they will adjust their voltages so that they can provide the 3 kV voltage, right? So this is the current. So the current will be according to the depending upon the load. What is the load? Now you can see that the voltage is the converter is trying to stabilize the voltage around 3 kV. So it will take time, but it will settle around 3 kV. Here our switching time is around the step time is around 0.0001. So yeah, this is how our system is working. You can see that it is perfectly tracking the DC voltage. So this means that our control is working very fine, and yeah, this is these are the submodule voltages. So the now submodule voltages are settling around 400. So in the simulation results, you can see that the previously when we have a reference 3.6, so the submodule voltages would according to that, right? The settle band was 430 to 490, right? Right. So these are output voltage, these are the capacitor voltages, and these are the circulating currents. Currently, circulating current is not provided, but maybe in the next session I can generate a circulating current for this and explain how I have done that. So it is working very fine. Let me stop this. See, it is stable now, uh, getting settled around 3 kV. So this is all about this model. If you have any query, you can ask into the comment section, or you can directly reach out. Thank you.